Hi, John. We'll get started here shortly. Thanks for your patience. All right, John, thank you for joining in today. I'm going to go ahead and get started. Let me share my screen.
All right.
Okay. Are you seeing that okay?
Yeah.
Thank you. All right, so let me go ahead into the weekly overviews. Okay. So did you get an article approved already for me for the project?
Yes, ma'am. I did one a couple weeks ago and one last week.
Okay, good. Then you're all set. I don't need to talk about what happens in the event you don't get an article approved because you already took care of that. So I did want to just take a few moments to start talking about the summary that you have to write. But we'll come back to this whole information periodically and talk about it. And before it's over with, I'll cover all of the information. But now that you've found an article or articles and got them approved, what you should be doing now is kind of working on reading the articles, right? And you might have to read through it once and then put it down and then come back to them and read through them again. um Oftentimes students tell me that the articles are challenging and some stuff doesn't make sense. That is totally to be expected, right? Here's the thing: your task is not that you understand every detail of the article. Your task is to tell me about the things that you are able to understand from the article and tell me how those things connect back to the classes. Okay. So you don't need to explain to me line by line what the article is about. But a nice explanation of the big picture of the article and how it relates to the class is what I'm looking for you to do. That's what a summary is, right? You explain the big ideas, right? And so what you're going to be writing for me as a summary is to be 2 pages in length, typed, double spaced. Okay, so it's not that you have to write a whole lot. And that's why I made you find articles that were fairly long so that you could, get enough material to write a 2-page summary. And it's 2 pages double spaced. So that means that it's not a whole lot that you're going to be writing about. I often tell students that the bulk of what you write should actually explain how the article connects to class. So, you give me the main ideas of the article, and then you spend, um, most of that summary explaining how things in the article are related to the class. And we'll talk about some ways that you can do that, because I don't suspect that anybody is ready to start the writing at this point, but just to kind of guide you so that while you're reading and making notes about what the article is about, you're also focusing on thinking about how you can connect that article to things you're learning in the classroom setting. All right. So I give you the actual first sentence that you're supposed to put in your summary here. Okay, and then what we'll talk about, here in maybe about 2 weeks or so, is like, how does the paper need to be formatted? All right, but right now you're reading, you're making notes about the things that you understand from the article and thinking about how you can tie that back into the class. All right, any questions about that?
No, I don't think it'll be too bad. Like you said, just make sure I can understand it enough to write. But
Yeah.
I'll get it.
Yeah, and I tell students too, it is not wrong to Like, let's say you're reading something in an article and you're not quite sure what it means, and you're like, okay, I'm gonna look this up. I want to see what is this about? What are they talking about here? That's perfectly fine. But you don't need to tell me about what the like if you went to an internet site or a book or something to help you understand what the article is saying. You don't need to tell me about that. Okay. You're not doing a research paper. Your job is to tell me about the article. How you figure out what the article is saying is totally up to you. But I don't need to know that you went to Wikipedia or you went to you used a high school physics book or anything like that. That's not part of this project. Once you figure out what the article is saying, tell me that. But you don't have to tell me how you figured it out. Does that make sense to you?
Yeah, sure.
Okay. All right. So in a couple of weeks I'll come back to this, because my thinking is that in a couple of weeks you'll probably be getting to a point where you've read the articles, your articles maybe once, maybe you're on your second time reading through, and you might be ready to start, writing your summary. And so I'll give some more guidance about it. But all of the information is here in the project details. But beyond how you get started with it, I'm not going to cover too much on the actual writing, because I want you to focus on reading it now and making good notes and thinking about how you can connect it back to the class. All right. So it looks like it's just me and you again here tonight, John, and I'm okay with that. Um,
Yeah,
last
that's fine.
week, if I remember, we focused on Newton's laws. If I'm looking at the weekly overviews correctly here, yeah, last week. And so this week we're going to continue looking at some of the important contributions that Isaac Newton made to physics and physical science by looking at gravity and looking at how he explained this gravity force and how he came up with the relationships and the formula that we use to explain gravity. Okay, so that's what we're going to be looking at in tonight. And I'll also be once we delve into gravity and we look at the formula and we look at some examples of using the formula, then we'll also kind of tie it back into some of the stuff that we studied for circular motion. Okay, and that's what you see here reflected in these objectives. So on your plate for this class this week, you have the discussion on gravitation that's due by Saturday. Don't forget, post your answers and then reply to 2 of your classmates. And then you have problem set 6 and 7. Both of these problem sets are on Newton's laws from last week. Okay. And then under required readings viewings, there's information on gravitation in chapter 6 in your CK12 textbook. And I have some videos there for you. And then I'm going to go into these supplemental notes. And then once I'm done with this, I'm going to go into the extra resources that I have available. And we'll look at a couple of sample problems and then some other material that I've made available to you as well. All right. So Newton's universal law of gravitation is a way to explain the force of gravity by looking at it from looking at gravity as an attractive force between objects. Okay. So, we've looked at gravity from the perspective of acceleration due to gravity, 9.8 meters per second squared down on planet Earth. We've looked at gravity from the perspective of weight, m times little g. But now what we want to look at is gravity as this attractive force between objects. And this is what Newton's universal law of gravitation helps us to explain. This attractive force that we call gravity that exists between any two objects in the universe. That's why it's called the universal law of gravitation, because it tells us that every object in the universe is attracting every other object in the universe. And if you want to understand how much that force of attraction is between any two objects in the universe, then we can do that by using this universal law of gravitation. So, and this is what Newton helped to figure out. You know, you might have heard the story of Newton sitting under the apple tree, the apple falls, hits him in the head, knocks him out. When he wakes up, he says, voila, gravity. Well, not actually, but you know, it's a nice, you know, it's a nice story about, you know, kind of like a fairy tale, if you will, about how Newton figured out gravity. But and actually, he didn't actually come up with the complete equation. He came up with some key elements of the equation, but because the idea was really kind of synthesized because of his work, that's why he's given credit for it. And so the formula in the box helps us to understand the force of gravity, F, between two objects. In this formula, the two objects are represented by the little m and the big M, the mass of each object, okay? So, and this notes package use little m and big M, but some textbooks use M1 and M2. So it doesn't matter, little m, big M, M1, M2. The idea is that to find the force of attraction, the force of gravity between any two objects, you need to know their masses, okay? You also need to know the distance between them. That's what R stands for. Notice though, in that formula, R is being squared and it's in the denominator of the formula, right? So you take the masses of the two objects, you multiply them, and you divide by the distance between them squared. And then you multiply all of that times this constant, big G. Big G is known as the gravitation constant or the universal gravitation constant, okay? So we'll look at the value of big G here momentarily, but this formula is extremely powerful because think about it. It doesn't matter what two objects you choose, as long as you know their masses and how far apart they are, you can figure out how much gravity exists between them. And you can do that for any two objects in the universe. So that's pretty important, given the fact that, you know, you think about the time frame that Isaac Newton lived in, we didn't even know a whole lot about the universe. And here he proposes this law and says that this is how gravity works throughout the universe.
That is crazy.
That is crazy, right?
Man.
Think about it. Yeah. And we know that this whole, you know, gravitational force between the Earth and the moon, for example, is what creates high tides and low tides, right? I mean, the moon pulls on the water, you know, on the Earth, and that creates, you know, the change in the tides. So, you know, this is an example of this gravitation force playing itself out, right? Because in the formula, M1 would be the moon, the little m would be the moon, and the big M would be the Earth. And then we just have to know the distance between them, and we could figure out how much, you know, how much pull, right? Another area where this whole pull of gravity, this force of attraction between objects comes into play, is weightlessness. Now, weightlessness is just a feeling. The objects involved aren't actually weightless, but it happens because if an astronaut, for example, is in a spacecraft that's free falling around the Earth, and the astronaut is inside the spacecraft, so they are also free falling around the Earth. So the craft that they're in is free falling and as it orbits around the Earth, and they are free falling because they're inside that spacecraft. Kind of like if your car is going 60 miles per hour, how fast are you going? 60 miles per hour, right? But if you're dealing with an object that, if you're inside an object that's free falling, you will feel weightlessness. You will feel weightlessness because you are also free falling, but you are not actually weightless. It's kind of like the situation where they say if you're in an elevator and the cable snaps and the elevator starts to free fall, you will feel weightless because you are inside an object that's free falling, so you are also free falling, right? So you experience this weightlessness sensation. Doesn't mean just because you're inside an elevator that's free falling doesn't mean you don't have any weight. It just means you don't feel your weight. Okay. Another example is this idea of microgravity, and that is when astronauts and other objects are in orbit motion. They feel some small accelerations that are not associated with gravity. Okay, and they call that microgravity. So these are two other scenarios where this idea of this gravitation comes into play, because the force that we're dealing with is gravity. So this is kind of like the next bit of material kind of like gives some type of historical perspective and helps you to understand how eventually we get to this whole universal law of gravitation. So it kind of starts out with our curiosity about the planets and how they move. So humans have always tried to explain that as much as they could, using the tools that they had available. Okay, and so the ancient Greeks studied the motion of the planets, but in their mind, they thought that the Earth was at the center of what we call our solar system, right? So they had what they call a Euro kind of they call it the Earth-centric viewpoint, if you will. Okay, and they call these planets wandering stars because they actually thought there were stars in the sky. They thought that there are some stars that stayed stationary, but they thought that there are other stars that wandered around, and so instead of calling them planets, they call them wandering stars. And then the ancient Greek astronomer Ptolemy tried to explain that by coming up with what he called epicycles. So he tried to track the motion of these wandering stars as they moved around the Earth. Well, we know that view, that Ptolemaic view, that's what they call it, Ptolemaic view, because they thought the Earth was at the center of it all. We know that that's wrong. Actually, the correct viewpoint is this heliocentric viewpoint where the sun is at the center and the planets actually revolve around the sun. But for a lot of human history, they didn't accept that. They didn't know that. But it took scientists like Kepler and Tycho Brahe to come along and have some better tools and do some better observations and analysis to help us understand that actually that these wandering stars are actually planets, and they actually move around the sun, right? And so the reason that Kepler is really important is because he laid the foundation that Newton utilized to help come up with our understanding of gravity. Okay, at least to start our understanding of gravity. Let me say that. Okay, Kepler was like very, very observant. He did a lot of data collection regarding the planets. He had lots and lots of information regarding the planets. And he took all of that information and he synthesized it in what is known as Kepler's 3 laws of planetary motion. Okay. Now, we're not going to really, I'm not going to really go into great depth about Kepler's laws. Just that one of the things that he knew was that the planets didn't move in circles. And I've used the idea of the planets moving in circles sometimes to explain orbit motion, but truthfully, they move in elliptical type orbits, right? And so that was one of the things that he figured out. Okay, that first law deals with the idea that the planets have elliptical orbits. His second law looked at the area that the planets covered as they moved around the sun. Okay, and so what he was saying is that if you look at the area that is covered as the planet moves over equal time periods, the areas are going to be equivalent. So in the picture, area 1 will be equal to area 2 will be equal to area 3. And that is because if you look at the time it takes to go from A to B, it would be equal to the time to go from C to D and E to F. Even though the areas look different in terms of their shape, if you figure out the actual area, those 3 areas will be equal. So that's what his second law focused on. And again, I'm not trying to get into that too deep. The law that I'm most interested in is his third law. And that relates the ratio of the periods to the orbit radii. Okay. And we talked about this idea of period and orbit radii when we looked at uniform circular motion. And so we'll see here shortly that uniform circular motion is also connected to gravitation. Now, the other thing that makes this third law important is that this is what Newton utilized. He utilized this relationship to help determine the law of gravitation. Okay, so Kepler was, you could call him like a planet fanatic. He had lots of data and information about the planets, but the question that he couldn't answer was why the planets orbit. He couldn't answer the question, what's keeping them up there? He could track them. He knew, about their the time that was involved. He knew about, how far they were, how fast they were moving, all those things, but he couldn't explain why they're staying up there. Why are they orbiting? Well, Newton came along and he used Kepler's work to help us understand why the planets orbited, and he called that gravity. And so he built on Kepler's work to formulate the law of gravitation. And the starting point was this relationship between the period and the orbit radius.
When most people, would they work for the church? That's right.
A
That's
lot.
why they had all the time.
No, honestly and truthfully, if you go back and look at the work by Kepler and Galileo's work is in there, because if you remember when Newton was doing his laws of motion, he relied on the work that Galileo did. So Kepler, Copernicus, and Galileo were 3 key scientists that Newton built on. And actually, they found themselves in conflict with the church. They didn't work for the church. Actually, Galileo almost got his head chopped off by saying that the planets revolve around the sun, because the viewpoint of the church back then was that the earth was the center of everything, because human beings, the pinnacle of God's creation, lived on planet earth. So if the most important thing that God ever created is on planet earth, everything else must revolve around that. That was the viewpoint of the church. And these scientists came along and challenged that. And it almost cost him a life. Galileo spent the latter part of his life on house arrest under the threat of the Inquisition, because he was challenging that viewpoint. In fact, he had to publish some of his work using, kind of like being hidden, right? Using a different name, or, like like a stage name, if you will, right? So that they would not know that the information that was being spread was through him. But eventually it caught up to him, and it almost cost him his life. But because he was so well respected by so many, they didn't execute him. They put him on house arrest for the latter part of his life. So no, they didn't work for the church.
Yeah.
A lot of this.
I'd like to read I don't know if they even got it, but I'd like to read a book about how Newton
Yeah.
came up with what he came up with.
Yeah. So I'm actually going to show you some resources that you can use to do that. It's not necessarily a book, but there's some resources that I've made available to you that can help you with that. Yeah, Newton was a pretty pretty interesting character, because in addition to his love of science and all of the great things that he contributed to us in science, he was a deeply devout and religious man. In fact, he believed that you know that he could use science to actually determine and interpret the Bible to know when when would revelation and the end times be fulfilled. He really believed that he could use science to do that. And he was kind of a recluse. He really kind of stayed to himself quite a bit. And in fact, a lot of his work almost didn't get published in the way that we know it, because he had to be convinced by some colleagues to share the work that he had been doing, because there was kind of this like competition between him and another scientist. And that there was a great deal of well, I would say maybe what we would call unhealthy competition going on back then too. Right? Everybody wanted to be first to get their information out. And so sometimes they use means to discredit other folk that really had no basis. And so Newton was up against some of that, and he kind of went into himself, but a colleague convinced him that he had to share his work. And ultimately that's why we know some of the things about what he was doing and the work the work that he was doing. And it became really, really important to the growth of our understanding, especially where motion is concerned. So in these extra resources, I always share this with you because this is a great way to get access to some additional materials. All right, let's see if I can get this to open up. There we go. So here are, and if you notice, I went into the extra resources. There's a folder for every topic. So I'm going in gravitation, and here you go. Okay. And now you were looking for some materials that, you want to read some more. This one that has all these links, there's some great links on, on Newton's work regarding gravitation here, and some nice videos. So you can take a look at that. These other items on this bottom row here just kind of go in and explain more of the law of gravitation, just kind of like summarize some things. So, if you want to know what is Newton's universal law of gravitation, it says basically that every object is pulling on every other object in the universe. That's a simple way to think of it, okay? And this is the formula that helps us to determine how much are they pulling, okay? And if we're gonna find this force, I like to use the big G. Like a lot of books will use F with the little g on it. Either way is fine. It's notation. It doesn't matter if we use big G or little g. The bottom line is this is the formula. But I put big G to remind me that I'm dealing with this constant, okay? So in this formula, if I'm finding force, I know my unit is going to be newtons. Why? Because we learned last week that if we're finding force, the unit in the metric system is newtons. And if I'm going to find this force, I need to know the value of this big G. That is 6.67 times 10 to the negative 11. And all of this right here on the right, the Newton meter squared per kilogram squared, that is the unit for big G, okay? So here's the number part of big G, 6.67 times 10 to the negative 11. Now, you can think about that's an extremely small number, okay? Now, this big G, that's not a number that Newton came up with. Newton came up with the M1, M2 divided by R squared. So he knew through his own work that if you multiply the masses, that helps you to figure out the gravity force. And if you divide by the distance squared, that helps you to figure out the gravity force. But this big G was actually discovered 100 years after Newton by a fellow named Henry Cavendish. He did an experiment to determine this constant, because the problem was that when Newton was doing his work, we didn't know the mass of the earth. Remember big M, little m? Well, you think in many cases, the big M is the earth because that's the biggest thing we're closest to, right? But when he was doing his work in, 1600s, early 1700s, we didn't, in the early 1600s, excuse me, we did not know the mass of the earth then. But 100 years later, we know the mass of the earth. So this fellow by the name of Henry Cavendish goes into a laboratory and does an experiment, and he's able to use that now, the mass of the earth, to help figure out this gravitation constant. So he can take the formula from, being where we can write equal to, okay? Because if you're going to write a formula, we needed this constant of proportionality, and that's what he figured out. So this universal gravitation constant is an extremely small number. Well, see, that what that tells me is if I'm using everyday objects, the mass of everyday objects is way too small. So for example, let's say I look at 2 apples. I want to know how much. I got 2 apples sitting on the counter. They're 1 meter apart. So I know the mass, if I make the apple the largest as possible. Let's say I make the apple humongous, 100 kilograms. And both of them are 100 kilogram apples. If I put their masses in, 100 kilograms times 100 kilograms, 100 times 100 is what? 10,000, right? If I'm not mistaken. Yeah.
Yeah.
10,000. Now, 10,000 is 10 to the 4. If I multiply 10 to the 4 times 10 to the negative 11, I'm still getting 10 to the minus 7. That's way too small to have any noticeable effect, meaning that apples aren't going to just automatically, snap together like they were magnets or something, because the force of gravity between them is way too small to cause any effect. All right. But if we start using big objects like the earth, okay, let's take that same 100 kilogram apple times the mass of the earth, which is 10 to the 24 kilograms. Now you have something to work with to cancel out some of this negative 11. So you need big objects to be able to notice this force. And part of that issue was for Newton was that he didn't know the mass of the earth. So he couldn't write an equation but he could figure out relationships. And that's what you'll see in some of the material that I listed on that sheet if you wanted to go read, about the background of how he figured out this kind of stuff. Okay. The other important thing about this formula is that it deals with what we call an inverse square law. An inverse square law means we're looking at the distance squared, but it's in the denominator of our fraction. So inverse means 1 over, and it's being squared. So when we're looking at this gravitation force, the distance is important, but it doesn't go 1 for 1. What do I mean by that? So let's say I take those same 2 apples and I move them twice as far apart. Well, if you say, okay, I moved them twice as far apart, so the force should be twice as weak. But that's not what this inverse square law says. They're twice as far apart because that distance is being squared, the force is 4 times weaker. Why? Because if they're twice as far apart, that's 2. Square it, that's 4. So the force is 4 times weaker. Okay, so that's how an inverse square law works. And a lot of things in nature obey an inverse square law. Okay, we can think of this force of gravity being relevant for big objects, but even small, tiny objects like electrons and protons obey an inverse square law. So there's this kind of symmetry going on in nature, if you will. Okay, whether it's big or small. And so, this knowledge that nature was obeying this kind of inverse square law is what ultimately set Einstein on his quest to explain the forces that we see in nature. Recall last week I showed a chart that talked about the 4 fundamental forces of nature: gravity, the electromagnetic force, the strong nuclear force, the weak nuclear force. Well, Einstein believed that all of these forces were just parts of a much larger force that explained everything. And what led him to think that was the fact that large planets and small electrons obey an inverse square law. And we're just not getting to the point in our understanding of nature to be able to come up with this whole unified view of forces. But that's a whole other subject that's way beyond what we want to get into in this course. What we need to understand here is that this gravitational force is an attractive force between objects that obeys an inverse square law that grows as the masses of the objects grow. And this constant of proportionality that helps us to understand this force throughout the universe, this constant, big G, doesn't change, and it's extremely small. That's why the gravity force is such a weak force. Okay. All right. So now, what's the difference between this big G and little g? That's important, right? Because we're saying that big G is like this constant that deals with gravity, and little g is this important thing related to gravity as well that we've looked at. So what you have to remember, though, is that big G is a constant. It is the same throughout the entire universe, whereas little g is for a particular location. So it's not constant. In fact, for example, on Earth, little g is 9.8 meters per second squared. But on the moon, it's only 1.7 meters per second squared. So little g can change, but big G is the same whether you're on the moon, the Earth, or anywhere else. Okay? So you have to remember that when you're using this, that there is an important distinction between the two, and not make the mistake of putting little g in the formula. And then, this just explains that that the masses of the objects M1 and M2 are little m and big M, whichever notation you like. They're both in kilograms, and the distance between the objects is measured in meters. And of course, as you move the objects further apart, the force gets smaller. And as you bring objects closer together, this force of attraction gets larger. Okay. And then we'll look at, when we look at a couple of example problems here in just a moment, the connection between weight and this gravity force. Okay. So that takes care of all the extra items that I have on this bottom row. Remember, this document here, if you click on these links, that make for some good reading if you want to know more about some of the background regarding gravitation.
All right, thanks.
Yep. So what I'm going to do now is I'm going to do 2 example problems for you using the gravitation formula. And then we'll finish up by looking at the connection between circular motion, satellite motion, and gravitation. Okay. So in this first example, it said, determine the force of gravitational attraction. So in other words, how much are these objects pulling on each other between the Earth, and there's the mass of the Earth, 5.98 times 10 to the 24 kilograms, and a 70 kilogram physics student. Okay, so we want to know how much these 2 objects pull on each other if the student is standing at sea level. Okay, we know that's not Louisiana because for the most part, we're below sea level here, right? So at sea level. And if the person is standing at sea level, the distance from the center of the Earth, because that's where you measure from. You measure from the center of the Earth to the center of the student. And since the student is so small compared to the Earth, we just use the radius of the Earth, which is 6.38 times 10 to the 6 meters. Okay. So we have the masses of our objects in kilograms, and we know how far apart they are. So now we just need to substitute that into the formula. Okay. To find out this force, we put in big G, you see 6.673 times 10 to the negative 11, and they put in the units here. I wouldn't have put all that in, but it's nice that you can see how things cancel out, because I know I'm finding force. And if I'm finding force, what should my unit be? Newtons. So when I finish, I'm going to get newtons. Okay. So I put in big G, here's M1, here's M2, and I'm dividing by the distance between them squared. Okay. Now, I don't have one of those fancy calculators. So here's how I approach it. And the reason I do it that way also is because there's less chance for me to make a mistake if I do it this way. If you have a fancy calculator and you don't know how to group things properly, you will get the wrong answer. So be careful. Okay. So I take out all the numbers, and then I take out all the exponents, and I do each of those things separately, and then I combine them together at the end. Okay. So now what I do is I pull out all the numbers: 6.673, 5.98, and 70. There you go on the top here. And then I divide by the numbers on the bottom: 6.38, but it's got to get squared. Okay. Everything's getting squared here on the bottom: the number, the exponent, and the unit. All right. But I'm just looking at the numbers right here: 6.38, and it's squared. So if I multiply my top numbers and divide by 6.38 squared, I get 68.6. So 6.673 times 5.98 times 70 divided by 6.38 squared. That gives me 68.6. Then I have to do my exponents. Okay. So 10 to the negative 11 times 10 to the 24. Those are the exponents that I have on the top. And then on the bottom, I have 10 to the 6. But remember, it has to get squared. So in this exponent stuff, you got to remember the rules for exponents to do this. So you take 10 to the negative 11 times 10 to the 24. When you multiply exponents, you add. So that becomes like 24 take away 11. That's 13. So on the top part of that, I have an exponent 10 to the 13. What about on the bottom? I have 10 to the 6, but it's being squared. When I square an exponent, I multiply. So that becomes 10 to the 12. That's 6 times 2, right? So now on the top, I have 10 to the 13. On the bottom, I have 10 to the 12. When you divide exponents, you subtract. So that becomes 10 to the 13 minus 12, or 10 to the 1. So from my numbers, I have 68.6. From my exponent, I have 10 to the 1. When I multiply 68.6 times 10, because that's 10 to the 1 is 10, I get 686. So this 70 kilogram physics student that's standing at sea level on Earth is being pulled with an attractive force that we call gravity, 686 newtons. Okay. So now we use gravitation to figure out how much the Earth is pulling on this student. Well, last week we learned that weight is what? How much the Earth is pulling on this student. So let's see. How do we find a student's weight? The formula for weight is what? M times little g. So 70 kilograms times 9.8 meters per second squared. If you multiply that out, shouldn't be a surprise, but you will get 686 newtons. So when this student is standing on the Earth at sea level, the gravitation formula and the weight formula give you the same value. Why? Because weight is the force of attraction between an object and the Earth, in this case, the 70 kilogram physics student. So they're equivalent. That's because the student is standing on the planet. Let's look at an example where, so before I go forward, does that make sense to you?
Yeah. Mhm.
Yeah. So now let's look at an example where that's a little different, okay? So it says here, sorry, let me adjust that a little bit. There we go. Determine the force of gravitational attraction between the Earth and the 70 kilogram physics student if the student is in an airplane at 40,000 feet above the Earth's surface. So not at sea level, not even on the planet, 40,000 feet above the Earth. And this time that means the distance is 6.39 times 10 to the 6 meters, right? So farther from the center of the Earth. And you might be looking at this going like, okay, wait a minute, 6.38, 6.39, whatever, right? But no, we have to be careful, because what we need to do is go ahead and put that stuff in the formula just like we did before. All the numbers on the top are the same. The number on the bottom is 6.39. That's being squared. The exponents are exactly the same. But when we do the math, this time we get 684 newtons. Okay. So you can see when that person, the 70 kilogram physics student, is flying in an airplane 40,000 feet above the Earth, it's not 686 newtons anymore, it's 684. So it's less. And here's the thing. You cannot do W equals M times little g. Why? Because they're not on the planet. So W equals M times little g to get the weight is only useful on the surface of the planet or the moon or whatever, right? Wherever they're at. But you can use the gravitation formula anywhere. Why? Because all you need to know, what are the masses of the objects and how far apart they are. See, that's the beauty of Newton's universal law of gravitation. You can find the gravity anywhere. Weight is only relevant if you're on the planet. Okay? So, this is why this law is so important, because it allows us to figure out the force of attraction between objects, beyond being on planet Earth, beyond being on the moon, or on anywhere in the universe. That's the beauty of it. Okay. So, putting a rocket in outer space It's possible because we understand how gravity works out there. Okay. All right. So what I want to do next is I want to look at these last two pictures, the one on the far left and the one on the far right. I'm going to start with the one on the far left with the red writing on it. But let me say this right up front. I'm not tasking you to understand any of the math that I'm doing in the red writing. I just put it there to guide you and help you understand how we got to this point, okay? So if you recall, prior to midterm, well, let me think. Yeah, I don't think y'all had, this class had the information about the satellite on the midterm exam. I think we covered that after midterm exam with you for you guys for this class because of the timing issue. But we have covered a circular motion because I know I did the example of which satellite moves faster, the Leo or the Geo. I did that example with you. And so that relies on our circular motion formulas. If you go back and look at the circular motion formulas, we have a circular motion formula to find the speed, 2 pi r over t. And we have a circular motion formula to find the acceleration, v squared over r. Remember, centripetal acceleration, v squared over r. What we didn't do was take Newton's second law for circular motion to get force. So now that we know Newton's second law, we can figure out the centripetal force. Well, what does Newton's second law say? Force equals mass times acceleration. So I'm just going to apply that to circular motion. Centripetal force equals mass times centripetal acceleration. So Fc in the box, I'm doing right here in the box, right in the middle, Fc equals mass times AC. Centripetal force, remember, centripetal means toward the center, right? Toward the center of the circular path. So this object experience that is moving in a circular motion orbit experiences a force toward the center of the circular path. All right. And so now we can take our definition for AC and substitute it. So that's how we got mv squared over r. Okay. Because AC is equal to v squared over r. So I just substituted for it. So now I know if this object is moving in a circular orbit path, I know the speed, the acceleration, and the force. Okay. But if it's moving in a circular orbit motion, the question is, what's keeping it in orbit? Well, gravity, right? That's not difficult to understand. That what is keeping the Earth in its orbit around the sun? Gravity. What is keeping the International Space Station in orbit around the Earth? Gravity. So this centripetal force is being provided by gravity. And that's what I'm doing here in the red writing here. Fc is equal to F gravity, okay? Because gravity is what's keeping it in its circular orbit. And then I just did some algebra and so on and so forth, okay? But that's not what's important there, because I would never ask you to do that algebra. What you need to process conceptually about this is this centripetal force is equal to the gravity force, because gravity keeps the object in orbit. Well, if gravity is keeping the object in orbit, then we have an additional way that we can find the speed, we can find the acceleration, and we just looked at the gravitation formula to find the force, okay? So this centripetal force, mv squared over r, is equal to my gravity force, okay? And so out of that comes another way to find the speed. I can find the speed by doing 2 pi r over t, or square root big G times big M over r, where big M is the mass of the planet. Whatever planet you want to figure out. Tell me how far away that object is from the center of the planet, any planet, and tell me the mass of that planet, any planet, and I'll tell you how fast the object will orbit. What about the acceleration? Well, I could do v squared over r the way we've been doing it, or now because of Newton's law of gravitation, I have another way to find that acceleration, big G times big M over r squared. Well, remember, big M is the mass of the planet. What planet? Any planet. As long as you know the mass of that planet and how far the object is from the center of the planet, you can find the centripetal acceleration. So you can see that that's really powerful if you want to put an object in orbit, like a satellite. Okay. What about this last formula? The period squared is proportional to the radius cubed. Well, remember I told you Kepler's law looked at what? The relationship between the period and the orbit radius. And it is from this relationship on the bottom, the period squared, is proportional to the radius cubed. It is from this relationship that Newton was able to build his law of gravitation. Okay. So we have two ways to look at orbit motion: circular motion or gravitation motion. And this last picture is just the same information without the red writing. Okay. So that's basically what I wanted to share with you from this, to look at some examples and then talk about the connection between our old circular motion stuff and our new gravitation stuff. And then just some, kind of summary notes and reference material, right? What
All right.
questions do you have of me?
The only questions I would have, and I, I might not even have them yet because I didn't finish, was from the lab, because I think the lab's ahead a little bit.
I don't know. It depends on which lab you're in.
Okay. Um, True, you're right. Let's see. I wrote down. Uh, okay. The lab we're doing work and energy,
Yes. Okay. So that means you're in.
and that is a really long.
Yes, that lab is involved. So let me go down to. There we go. Working energy, right?
Mm-hmm.
Okay. So here's the thing about this, and let me kind of break it down. So you, hopefully you were able to follow my instructions there, not to worry about the Logger Pro and any of that other stuff. Just, you're gonna use the simulator. So I think a lot of times that the challenge is using the simulator. So you have to know how to collect the data on this. Okay. So I'm gonna open the experiment handout as well. Okay. And so once you go out to the simulator, play around with it for a while. This first one is, it tells you that you're dealing with uh, conservative forces. Okay. So we're doing the intro part. We're not dealing with any friction or anything. So when you put this skater up here, what you have to do is you have to catch their data point when they come back to that side. See, like they swing to the right, back to the left, and it tells you in the experiment handout to collect the data point at here, 0 meters, 6 meters, 2 meters, 4 meters, right? So what you're doing is basically when the skater comes back, then you pause it. So let's say 4 meters. So you collect the speed and the height, right? And also on this, you're collecting the time because you're using like a stopwatch. So you start the stopwatch, and then the skater's going, and then when they come back, you pause it. So pause, 0 meters, how much time, how much speed, you got the height. And then you can, like when they come back, you want to pause it on 0 meters here, 2 meters here, so you got to really be quick on the trigger finger to catch them, right? I'm using a mouse pad, so it's not like I have a mouse that I can click, but that sometimes causes problems for students. And you only want to collect this, like, let them run for about a minute. Okay.
All right.
Okay. So now once you have like for about a minute, you collect the times at 6 meters, 4 meters, 2 meters, you write down the speed. Once you have that, you're going to use that information to complete this bottom table on step 6. And what I provided for you were the formulas that you needed. So I showed you right here. You see, help with the energy calculation. So if you open that document, it tells you for part 1, use this formula for the kinetic energy. So put in your mass and your velocity into this formula at every point and calculate the kinetic energy to calculate the potential energy at every point, at every height. Put
Stop
in,
sharing.
oh, I'm sorry, my bad. Let me see if
Oh, no problem. There it is. Go
yeah,
ahead. Well,
I didn't realize you weren't seeing the simulator at all, right?
I wasn't in it stop, so I don't know what happened.
Okay, so let me share again, because that's what's happening there. You're not seeing that. Now you should be seeing that sheet.
Yes, man, that's it.
Okay, so now this is I gave you the formula sheet that you need to use to fill in the table where they ask you for the kinetic energy, potential energy, and total energy. I think that's step 6. Okay, so for every data point, find the kinetic energy using the mass and the speed. Find the potential energy using the mass and the height. And then to get the total energy, you just add those two together. Okay. So let's take a look at what that looks like on that on the experiment handout. Bear with me for a second, because I'm gonna have to stop share and then I'm gonna have to share again. Okay. And I will open the experiment handout. So are you seeing that?
Yes, man.
Okay. So you see the first table, you're just collecting the time, the height, and the velocity. In the second table on step number 6, you're writing down the times that you have, the potential energy, and I just showed you the formula that you need for that. The kinetic energy, showed you the formula you need for that. And then you just add those two together to get the total energy. Okay. Then you're going to go to this next table where you're doing non-conservative forces. So see, it tells you click on friction. Okay. So now let's go into the simulator and we'll click on friction. Now the challenge with this one is that the skater is not going to just keep going back and forth. The skater is going to slow down and eventually stop because there's friction. Okay. And so when you put the skater here, if you notice, you watch, they don't come back to the same height. Okay. So what I always tell students for this one is, it might say 45 seconds, it might say a minute, but it's not going to take that long before the skater comes to a stop. So just collect as many data points as you can. All right. So, you put them up here starting at 6, when you let them go, they're not going to come back to 6 because they'll lose energy. So, you just pause it as best as you can. Okay. So then you got to let them go and catch it. Right. And so see, at each stage, they're going to go lower and lower. So eventually it won't even take a minute for them to stop. All right. But however many heights you can get, however many times you can get the speed, you record those values. Okay.
All right.
Once you have recorded those values, then let me share again, because I got to go back to the experiment handout. Let me see. Okay. This is kind of in my way right there. Okay, so once you have those here, you see it says 45 seconds. It's not going to take that long.
Yeah.
So you won't be able to fill this table. So don't worry about that. And this one, then notice here, you're calculating that you have the time values that you measured from your stopwatch. You can calculate the potential energy values, MGH, kinetic energy values, 1/2 mv squared, because part of what you're collecting is the height and the speed, right? Now, the question then becomes, how do you calculate these things? Okay, so I've given you a sheet to help you with that. So let me stop share and bring up that formula sheet again. Share. Let me bear with me for a second, because I want to make sure that's on the screen, because if it's not, it won't, you won't see it when I do it. So let me bring this up, and now let me do share the screen. And let me do this. Are you seeing that?
Yes, man. I think so.
Okay, so see, now go down and find part 2. So I'm telling you, for part 2, the kinetic energy is 1/2 mv squared. Potential energy is still mgh. But to get the thermal energy, I call it THE, thermal energy. You have to take the total energy equals to the kinetic energy plus the potential energy plus the thermal energy. But the question is, how do you get that thermal energy? So you can take the total energy minus the kinetic energy plus the potential energy. So there's the key here is that the total energy is always going to be what you found from the start. So when the height is 6 meters, the total energy is mgh, mass times gravity times 6 meters. And that's the same total energy that you're going to use every time in this formula. Okay. And so all you're doing is you're subtracting out the kinetic energy plus the potential energy. And that's how you will get this value in the table. All right. So you can use this sheet to help you do the calculations that's required in that experiment handout. Okay. Let me share this, and then I'll minimize this. So in this experiment handout, notice this you can calculate these values using the formula that I gave. This total energy is always the same. M times G times 6 meters. It's always the same. But to get this one, you have to subtract out these two from this. Okay. And then the last thing, they ask you to make graphs. So you will have 2 graphs. You will have a graph that you do. Let me go back up. You will have a graph that you do in step number 7. You're going to graph all 3 of these things on the same graph. In your graph, you see they tell you the time goes on the x-axis. This and this and this go on the y-axis. So you're going to have 3 separate lines on the graph. One for potential energy, one for kinetic energy, one for total energy. All 3 of these get plotted on the same graph with time on the horizontal, and each one of these gets plotted separately on the vertical, but all on one graph. And then when you get down to this step right here, you're going to do another graph, and this time you're going to have, it tells you the time on the x-axis, and then each one of these graphed on the y-axis using the same graph. So you should only have 2 graphs, but you'll have maybe like the time potential energy might be, you might use red, kinetic energy might use blue, thermal energy you might use black or green or whatever, different colors to show that you're plotting these different values but on the same graph. Does that make sense to you?
Yes, ma'am.
Okay. All right. Now, and again, don't worry about anything where it talks about Logger Pro or any other kind of software, or anything like that. Please don't worry about that. Don't worry about using any other kinds of software, anything. You only need the simulator to do this. Collect your data, fill in your tables, make your graphs. And then I don't know, let me see if what I had you do for the lab report on this one. Yeah, you follow your basic template for a lab report. All right. So if you're working at any point, John, don't hesitate to reach out to me. I'll be happy to respond to any emails, regarding your questions.
Good thing I will.
All right. Well, look, I appreciate you joining in this evening. Have a good one. Looks like the worst of the weather is past
Yeah,
us. So
pretty much, huh?
yeah, enjoy whatever remains of your day and stay dry.
Well, thank you, ma'am. I had a good time.
All right. Take care.